Welcome to video number 2. This one will be about the exponential decay scenario. So in this scenario, we're going to consider some illness that is plaguing a town, that kills the population of a town. Let's say this is what we know. The town consists of, 2,000 people. It's a tiny little town, like Stars Hollow, small little town. And let's say that we know that each week the illness is going to kill 7% of the population. We want to write an equation that's going to model the situation. So we want some P of t equation that will model the population. At t weeks. So let's make our table again and consider that situation from the beginning. So if we have our table, again, we're going to have a t, this time in weeks, and a P of t that will be the population. So at week 0, there are 2,000 people in the town. After 1 week, we have lost 7% of the population. So first, we're going to want to figure out what is 7% of that population. Well, if we do 2,000 times 0.07, we get 140. We get 140. But it is not that 140 people are left in this town. That is the number of people that have been killed off by the disease. So the number of people left in this town is 2,000 minus the ones that we figured out that were killed off, which is this 140. So then we want to do 2,000 minus 140. And in this case, we get 1860. All right, and here's the moment where I stop being cute with it and we go back to looking at this equation and this formula. In this same scenario, we had 2,000, the original population, being multiplied by 1, minus 2,000 being multiplied by 0.07 to being the people that were killed off. So again, I'm going to distribute and pull this 2,000 that's common in each term out in front. I've got a 1 in my first term left over, and then a minus in between, and then 0.07 left from my second term. So really, what I'm doing in this situation is I'm saying 2,000 times 0.93, or 93%, which is like the complement of this in this case. If 7% of the population is killed, 93% of the population continues to lives on. So rather than thinking about the people that are killed, we're going to think about those people that are left that live on. So essentially every time what we're going to do from here on out is multiply by 0.93. And yeah, sure, people are still dying and my population is still going to get smaller, but at least now I'm considering the amount of people that are left and making my algebra work a little bit shorter for myself. So after 2 weeks, there are 1,804 people left. After 3 weeks, there are 1,677 people left. After 4 weeks, there are 1,560 people left. And finally, after 5 weeks, there are 1,451 people left. So town's dwindling, but not hugely. Again, if I wanted to know months and months in the future, because I'm trying to predict whether or not it's even worth it for people and doctors to go in and provide resources to try to fix this, let's say I want to know about t really far in the future. Like let's say t equals, 30 weeks down the road. It's pretty far. How many people are left? Are there even people left? Are we at a zombie population and just like a ghost town? what I'm thinking about doing there is I have my original 2,000, and I'm going to multiply by 0.93, by 0.93, by 0.93 over and over and over again until I have exactly 30 of those. 30 times. So what that means is that I'm taking my 2,000, I'm multiplying it by 0.93 raised to the 30th, because that is how we say repeated multiplication of 0.93 30 times over. So I can generalize this situation to be a P of T for the population that starts at 2,000. 7% get killed off, or 93% remain, raised to the T to tell me how many weeks. And then I can plug in any value of T that I'd like to know exactly how many people would be alive in the given week. Hopefully this helps you to complete the amoxicillin or other exponential growth decay problems that you may be working on.